The shape of the universe, the beginning. The lambda CDM model gives us amazing calculations with matching real-world measurements. We have a pretty good understanding of how our third-dimensional universe came to be after the Big Bang, thanks to relatively recent additions to the model like cosmic inflation. In 1964, scientists discovered the cosmic microwave background radiation, which confirmed a key prediction of the Big Bang theory. This led to the acceptance of the idea that the universe began in a hot, dense state and has been expanding ever since. During the 1970s, scientists focused on models that relied mostly on baryonic matter, the stuff that makes up atoms, but they struggled to explain how galaxies formed given the small variations in the CMB. In the early 1980s, they realized that introducing cold dark matter, CDM, in larger quantities could resolve this issue. In the 1980s, research focused on models with cold dark matter and critical density, with around 95% CDM and 5% baryonic matter. These models successfully explained the formation of galaxies and galaxy clusters, with decent accuracy. The model gained prominence after the observations of accelerating expansion in 1998. Subsequent observations, such as the Boomerang experiment and the 2DFGRS Galaxy Redshift Survey, further supported lambda CDM by measuring matter densities close to the measured critical density, and revealing the presence of dark energy. More precise measurements of the CMB from spacecraft missions like WMAP and Planck between 2003 and 2015 continued to support the model, and helped narrow down parameter values with high precision. Currently, active research is ongoing to refine the parameters of the model, and resolve any remaining tensions between it and recent observations. Let's begin exploring the timeline of the third-dimension universe, starting from its earliest stages. Our universe's journey spans two eras, the radiation era, and the matter era. The radiation era begins with the Planck epoch, which only lasted 10 to the minus 43 seconds. During this time, the temperature was a scorching 10 to the 40 degrees Kelvin, and there was no matter, only pure energy. At this time it was many times smaller than a single proton. The grand unification epoch sees gravity and the strong nuclear force emerge, and lasts until 10 to the minus 36 seconds. The inflationary epoch rapidly expands the size of the universe, starting at the size of a single atom and doubling in size at least 80 times. This causes the temperature to drop from 10 to the 40 degrees to 10 to the 33 degrees Kelvin, but this is still far too hot for atoms to form, or even light photons to escape the churning plasma. The electromagnetic and weak nuclear force emerge in the electroweak epoch, which lasts until 10 to the minus 12 seconds, still a tiny fraction of a second after the initial Big Bang. Quarks start to form for the next 10 to the minus 6 seconds, in the quark epoch. The temperature is still too hot for any cohesion, so the quarks stay unbound. Finally, from 10 to the minus 6 seconds up until 1 second, quarks come together and protons and neutrons form in the hadron epoch. For about 2 minutes, they undergo changes that set the stage for further transformation. Finally, after the first few moments were over, for the next 50,000 years, the nuclear epoch sees the temperature continue to drop and nuclei form from protons and neutrons. In the hot plasma, atoms of helium form and fill space. At the end of the nuclear epoch, the radiation era comes to an end as well, and the universe moves into the matter era. For 200 million years during the atomic epoch, once the temperature finally cooled enough, electrons start to bind with nucleons, forming new atoms of hydrogen. This also makes space transparent for the first time, and light can finally escape. The first light of the universe is still detectable today, and is known as the cosmic microwave background radiation. For 3 billion years afterwards, the galactic epoch seeded galaxies, as molecules gravitated to each other and started to grow stars and galaxies. From that time until now we have been in the stellar epoch. The temperature of space has significantly dropped, to 2.5 degrees Kelvin. That's just a couple degrees above absolute zero, or about minus 270 degrees Celsius. About 5.5 billion years ago, dark energy became the dominant force in the universe, increasing the accelerating pace of the expansion of space. In our solar system, the Sun started to burn about 4.6 billion years ago. Enough hydrogen and helium collapsed together to start the fusion reaction that has been burning ever since. Only 100 million years later, planets and asteroids formed from dust and gas clouds circling the Sun. The Earth's surface is bombarded with asteroids for a few hundred million years, adding new elements like ice and metals to the churning surface of volcanoes and molten lava. The volcanoes spew carbon dioxide, which makes up most of the atmosphere, along with some nitrogen. Finally, the bombardment ceases and the crust hardens, creating collection points for water, and oceans and lakes form. 4 billion years ago, in the ocean below a carbon dioxide-rich atmosphere, single-celled organisms with no nucleus begin the long journey towards life. Photosynthetic bacteria grow on the surface of the ocean, using sunlight, water, and carbon dioxide as fuel, releasing glucose and oxygen into the atmosphere. Nearly 2 billion years later, the first cell develops a nucleus and single-cellular life begins. For another billion years, the single-cellular life and photosynthetic bacteria turn a toxic carbon dioxide atmosphere into a livable one for carbon-based life. Multicellular organisms didn't start forming until around 800 million years ago, and it took most of the time since then for our species to split off from the family tree. It wasn't until 2.8 million years ago that the first genus appears, and it took the next 2 million years for them to harness fire. 200,000 years ago, Homo sapiens sapiens emerged from the family tree, amid 6 genus cousins that were around for another 175,000 years. With better intellect and communication, came better ways to improve knowledge, and 50,000 years ago innovation exploded and complex cultures started to emerge. Civilizations started to form over 10,000 years ago, around the same time the other genus cousins died out. Our earliest recorded history is about 7,000 years old. All of recorded human history fits into this 7,000 years, even what we consider to be our ancient history. The scientific revolution started 500 years ago, and for the next 450 years after, our knowledge grew increasingly steadily. But with the invention of computers 50 years ago, the computer age has exponentially grown our understanding of math and physics, the internet has made knowledge more accessible, and space exploration has become possible. Today we have more than 7,000 satellites orbiting the Earth. All of this is just the beginning of the third dimension universe that we live in. In context of the nested spheres model, that is just the center sphere. The 2 outer spheres, since they have their own space-time dimensions, will also have unique timelines and their own beginning story. Since we don't have a CMB for the 6th dimension or 9th dimension, we can use existing theoretical frameworks and thought experiments to try to imagine how they would have unfolded. Since they are all separated with their own space-time dimension, time in one dimension may not be directly connected to time in another. For example, from the perspective of the 6th dimension, the likely amount of relative time between the first instance of the 3rd dimension and the current instance would be 0. All possible 3rd dimensions would have branched out in an instant, with ours being one of the many. In our 3rd dimensional time, it may have taken 10 to the 2.5 million years for the Big Bang to occur, but from the 6th dimension it makes no difference. If it can exist at all, it instantly becomes part of the multiverse in the 6th dimension. The framework of the 9th dimension is essential for the other dimensions to exist. And the same can be said about the 9th dimension as the 6th. From the perspective of the 9th dimension, the amount of relative time it took for the lower dimensions to appear is 0. Conditions in the 10th dimension would have needed to be perfect for such an event to occur, but even if it took 10 to the googolplex years, if it can happen at all, it will eventually. If the universe simulated itself into existence, then it would have started in the higher dimensions. According to string theory, our universe emerged from higher dimensional space, with the extra dimensions being compactified and hidden from view. The nested spheres model is an incredible tool to help visualize how these dimensions could be interacting with each other, and how they could have formed our 3rd dimension universe.